Before I get into this here, I want to mention that there's a lot of complex and detailed history that goes into the things with interest rates and values of investments that I'm not going to get into in this class. It's a topic for somewhere else, a different context, because we've got a lot to do here. But just bear in mind that there is quite a bit more that goes on into here than these three formulas. Anyway, if you're going to talk about making an investment like into a bank account, there are a couple of different ways that your money can grow, but it's always in terms of the interest rate, where the most simple scheme that you can deal with is, well, simple interest, which is the sort of thing you don't actually get in practice, except for maybe like if you're going to loan $5 to a friend and say that they owe you an extra $1 per week that they're late.
Look at it this way, it costs you $20 to get rid of him, right? He's never going to bother you again. He's never going to ask you for money again. He's out of your life for $20. You got off cheap, forget it.
Because for simple interest, the only way that the value there grows is in terms specifically and directly of your initial value and the interest rate. So this is actually written out as P times 1 plus RT, or P plus PRT, so the principal value plus the value of the interest there in terms of the principal, P times the rate times the amount of time it's built. Where, again, that doesn't leave a whole lot of room for growth. So usually what we talk about is things like compound interest, where some number of times n per period t, where usually we make t years, and then we can talk about n being something like once a month, so 12 times per year, or once per week, so 52 times per year, or once per quarter, so 4 times per year, and any number of values in that sort of scheme, that the value will both grow in terms of the initial investment as well as in terms of the interest grown to that point, where we can think of this as being something like getting our simple interest formula, but along with t additional factors for all the times that the interest will compound. We have to multiply in there a whole bunch more times to get what we're looking for, where, to be sure, a little bit of history here, actually collecting interest with a compounding scheme was once considered illegal. It's considered a very harsh form of usury because, even though it might not look like much here, it does cause the value to grow a lot faster. So for a very, very simple example, just so we get the idea of the type of thing we're talking about here, let's say that you make an initial investment P of $20, where you have a 5% interest rate, so R is 0.05, and T here is 100 years. Again, it's a little bit silly so that you have something for 100 years and that someone will give you 5% interest. Neither of those is very likely, but proven point. So if you want to follow simple interest, then what would end up happening here is your final value, A, would just be that $20 times 1 plus 0.05 times 100, which you multiply that all out, you add that all up, and you will get a shocking value of, here, $120. Because you're getting 5% per year for 100 years, 5% of 20 is $1, so you're getting $1 per year. It's not that bad, but it's also not that much. On the other hand, for compound interest, where if this is following a compound interest scheme that I'll call annual, that's probably the least advanced kind of compounding interest, where it's just that it grows one time per year, that it compounds once per year, call that annually compounding interest. We would instead have A equals 20 times 1 plus 0.05 raised to the power 100. So with something like compound interest, we're dealing with things in terms of exponential growth instead of linear growth. And as we said earlier, exponential things might not get off to the fastest start, but once they get going, Because here, following compound interest, the value of that investment would be about $2,603.03. That is a much, much bigger amount. Much, much more value would accrue in that case if we have compounding interest. We can actually take this another step further, but before I do that, I need to clean this up here and make myself just a little bit more space. So the way we can take this a little bit farther, the way we can go a little bit faster, is to understand that when we look at these compounding schemes, we don't have to restrict ourselves to annual or semi-annual or quarterly or monthly or weekly or daily or even like secondly compounding interest. It's a theoretical thing. We don't have to just let that stop at any fixed value. We can make that as small as we want to, make it happen as fast as we want to. Where if we set ourselves up with a very silly investment of a $1 initial value with an interest rate of 100% and have it be with n compounding periods over t years. Again, if you get 100% interest, don't put $1 in, put all your dollars in. It's a lot of money. But say we could do that, our value there in terms of n periods after one time t would be something like a equals the quantity 1 plus 1 over n raised to the power n. And so if we want to find out what happens to that for various types of compounding interest, we can plug in values for n, values that we know. So if that compounds once per year, that's annually compounding interest, n equals 1, you would get a is equal to 1 plus 1 over 1 raised to the power 1, which is a really fancy and stupid way of writing 2. Which makes sense, right? If it compounds only once in the year and you have 100% interest, you'd go from 1 to 2. Not super fun. But let's say you had better. Let's say that happens monthly. So in that case, n would be 12. So you'd have 1 plus 1 over 12 raised to the power 12, and that would give you 2.613. And then if you had weekly, that would be 1 plus 1 over 52 raised to the power 52. I don't know where the extra overs were coming from, but you'd end up with about 2.693. And then if you did daily, then you have n is 365, so you'd have 1 plus 1 over 365 raised to the power 365, or about 2.715 and change. And hopefully you're starting to see a little bit of a pattern forming here, and you could make n bigger to be even more sure for yourself, but you see this is getting closer and closer to being just 2.7. And what happens here is we're describing a thing that gets closer and closer to what's called continuously compounding interest, where continuously compounding interest is a behavior referring to the interest rate never stopping compounding. It's always, 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 always growing. And that, through the work of Jakob Bernoulli, was where a very special number was discovered. There was a very special value here meant to describe these types of things that is about 2.718, which we call E. So E is itself a transcendental value there. It is a number that's a non-repeating decimal. It's a lot like pi, except we use this letter here to honor the work done by a student of Bernoulli's brothers, that is Leonard Euler, where it's a little bit silly to call Leonard Euler Johann Bernoulli's student. No offense to Johann Bernoulli, he was a perfectly good mathematician in his own right, but Euler may well have been the greatest mathematician to have ever lived. There's a strong argument to be made for that case anyway. But for us, this is the context where his number here comes from in the idea of continuously compounding interest, where if we have a continuously compounding account, then the value of it after t periods will be p times e raised to the rt. And this is the sort of thing we talk about here with our main two kinds of interest, which we're going to see one example with next.